In this video, we're going to discuss the non-destructive inspection method known as magnetic particle inspection. Now, just before we discuss the test itself, it's important to understand a couple of things about magnetism. So on the right-hand side, we have a diagram and we have a device that's known as a yoke. And the yoke is basically an electromagnet. So when we switch on the yoke, it's going to have a north pole and it's going to have a south pole. So above the yoke we have a test piece, and in order for this test to be carried out, that test piece needs to be a ferromagnetic material. And by ferromagnetic, we mean it generally contains iron. So ferromagnetic materials. Now when we apply the yoke to the ferromagnetic material, assuming that there's no breaks or damage or defects on that material, then what we will see is a magnetic field setup with a north and south pole, similar to the yoke. And if we were able to see the magnetic fields, what we would see is field lines travelling from north to south on the outside of the magnet, and then south to north inside the magnet. So in effect, what we've done with the yoke is we've created a magnet. So let's remove our yoke for a moment, and then we can discuss what happens when there are cracks or defects in the material. So if there was a crack in the material, and with this test it can be surface cracks or cracks that are just below the surface, but if we had a crack running through the material here, then in effect we would be splitting that magnet into two separate magnets. We would end up with a new north and south pole at the centre here. Within the magnet, we would still have magnetic fields travelling from south to north, but outside the magnet, we would be travelling from north to south. And what we end up with is something called flux leakage. So we end up with a leakage of magnetic flux from the crack. And this is what makes this particular test possible. So the first thing that we need to do, as in the previous test, is clean the surface. And what we're trying to do here is ensure that we get good contact with the magnetic yoke, as well as removing any debris from the surface. We then apply the field, and as we saw before, we apply the field using the yoke. And when we apply the yoke, we end up with a north and south pole, and assuming there's a defect, we end up with north and south poles at the centre. The next thing we need to do is apply the particles. And the particles are basically made of iron, small iron particles, but they've also been dyed to improve their visibility. So we'll have a powder shaker or a dispenser, and we will apply the powder to the surface of our material. Now around the cracks, because of the flux leakage, we're going to get a higher density of particles. And in fact, some of those particles will even fall into the crack. So what we end up with is a much higher concentration of particles at the crack. We can then remove the field and those particles will remain in position. So once again, a certified technician would need to interpret these results. So they'd be looking for areas where there's an accumulation of particles and determining whether that's giving a relevant or a non-relevant indication. Now once again, what determines a relevant and a non-relevant indication would be dependent on industries, sectors, materials and so on, and that would be set out in standards or codes for each of those areas. So as an example, it might specify that a relevant indication is anything where the major dimension is over 1.6 millimeters. So in the case of our cracked surface here, the major dimension would be the top surface or the length of the crack on the top surface. And if this was over the given value of 1.6 millimeters, then that crack or that defect would require further investigation. Once again, it would be up to the certified individual as to whether they accept the component and allow it to remain in service, reject the component, meaning it needs to be replaced or taken out of service, or whether they can repair the defect. Now, a great example of where this is used would be offshore in the oil and gas sector, where we have very large pipe works that are often subjected to very high pressures. And what we can actually get as a result of the environmental conditions and the high pressures is something called stress corrosion cracking. And stress corrosion cracking would appear as small cracks on the surface of cylinders and pipeworks. Now, to the naked eye, it would be very difficult to identify these, particularly if they were sitting just below the surface. But with magnetic particle inspection, we would be able to identify these surface cracks and defects. And I'll show you an image of this in a moment. So just to summarise the test, the surface of the pipework would need to be cleaned. A magnetic field would need to be applied, creating north and south poles. The particles would then be applied, and we would see an accumulation of particles around each of these stress corrosion cracks. And then when the field's removed, the certified technician would be able to interpret the results to determine whether these were relevant or non-relevant indications. So this is an image from Wikipedia, and what we see along the bottom is a centimetre rule. So this gives us some sort of idea as to the size of each of these cracks. So the certified engineer has carried out the test, and what we notice is stress corrosion cracks appearing here and stress corrosion cracks appearing here. At this stage, we're unsure as to whether these are relevant or non-relevant indications, but that would be down to the individual to compare these against the codes of practice and determine whether these require further investigation.